Hi everyone. Can you hear me well? Okay, good. Um, First of all, yeah, thanks, Professor Gupta, and also Nicola Shamik, okay, for having me here. First trip for me in India. I landed Friday morning, very early morning, went to ICTS, and now I'm here at TFR in Mumbai, so I'm very excited. I know about this place from many years, and I've always wanted to visit. So this is a great opportunity. Thanks a lot. So I'm tasked to talk about some numerical methods and to solve quantum many-body problems. And then, of course, this could be related to evaluating correlations, long-range correlations, so on and so forth, which is the theme of the school. And I would like to highlight, first of all, maybe how difficult the problem is, and then I will talk about different methods. So I will spend quite a bit of time on tensor networks, and in particular in 1D matrix product states. I'm not sure how many lectures I will cover with that, but I have quite a bit of material, so we'll try to cover a bit of that. And then I would like to, and the tutorials that we will run will be related to this topic, and then it's been set up by Gautam, PhD student, is also here, and from what I understand, we will do this tutorial on Thursday. Okay. Another topic I want to talk about is another exciting topic in numerical methods for many-body quantum systems. It's neural network quantum states. Okay. So this will be towards the later part of my lectures. And I think in between, in case time permits, I will sneak in some tricks that are useful for exact diagonalization, which is very useful for smaller systems and to calibrate benchmark all the other methods for different skills. Okay, I will use the board all the time. Maybe in case I ran out of material, then I will use my laptop and some slides towards the end, but I hope I have enough material. So as Shamik mentioned, feel free to ask questions anytime, especially easy questions, okay? Keep the hard ones for later, okay? Okay, so most of the time I will talk about spin chains, and then maybe I can mention things about fermions or bosonic systems. But if you have questions specifically, how will this translate for fermions or bosons, feel free to ask. I will try to address, although most of my experience is with spin systems. And spin systems, you can, most of the time, maybe by default, without thinking about it, I would think spin halves. Okay, but of course we can extend it to spin ones, and we have a few works on spin ones, and they have also some very nice property. But let's say we have a spin chain, spin half. Okay, is this big enough for the camera, for the people behind? It's good enough. Okay, okay. Spin half chain or spin half system. Let's say we have a spin half system with n spins. Okay. So now, obviously, you can say this is a very large system, because if I want to describe it exactly, the setup, I will need 2 to the n, a vector of a size of 2 to the n, an Hilbert space of this size. And 2 to the n is actually something that grows really, really a lot. So to have an idea how difficult this problem can be, is if you think about a setup with about n equals to 270. Why did I choose 270? You figure out. So, okay. This corresponds to roughly 10 to the, anybody knows? No. Okay. So 10 to the 3 is about 2 to the 10, right? Okay. Okay. So 10 to the 81. Okay. Okay. So this is supposedly the estimate of the number of atoms in the universe. Okay. Actually, it's 10 to the 80 or something like this. I am not sure how they got to this number, but So it's a really, really large number. Okay, so now you see out there are announcements of quantum computers, for example, with even 1,000 qubits and so on. Of course, they are noisy, but let's say you have a proper computer with, let's say, 270 logical qubits. Okay, where you can do error correction, so on and so forth. Then you can simulate a really, really, really large system. So this is difficult. Now, it's difficult, but how important, how relevant this is. And the first thing maybe I want to say is that there is a difference between typical versus relevant. Okay? Some problems may be difficult. Okay? For example, if I want to study, I want to produce a generic quantum state, then it's really very hard to write. But there are many states which are relevant and which are not difficult to study. And this comes from interesting studies on area law, for example. And okay, so if you take a gap system, okay, so you find that entanglement will go as L to the D minus 1, where D, as we pick, is the dimensionality of the system. So in a sense, they're a little bit easier. You don't need L to the D. Then this is for gap states, ground state, but also thermostates. And as we can show later, it is systems with what we call area law, because it goes as the size in one direction to the dimension minus 1, so area law. Can be described, they require a lot less, information to keep. Now, so this is one thing. The other thing that is important.
For thermostat, are you talking about entanglement or other measure?
Entanglement.
Still source area law?
Sorry?
Still source area law?
Not for all systems, huh? I'm saying for gap systems, ground state, okay?
Even if you are in thermostat?
Yes, gap of gap Hamiltonians. Yes. Okay. So this works where some of these results go back to, for example, Hastings 2007, if you want to find more information. Okay. Now, the other thing that is important, and maybe it's something that I should mention here, since I may miss sometimes to give references, but a lot of what I'm going to talk about here today is based on 3 reviews that I found quite important. There are many reviews, but 3 that I found, maybe because historically that's when I was starting to study this topic. One review is by Scholbock, 2005. It's an RMP. Another one is Scholbock again. It's written with a 2 dot. 2011, Annals of Physics. And then one by Urus. Urus had a few, but the one in 2014 is the one that I follow quite a bit. And then, of course, you can find a lot of nice information on the internet, especially when you look for some libraries, libraries that are very nice and useful. One is iTensor. And I think you will play with iTensor during the tutorial. And if you look in iTensor, you find also some information about these things. And then TemPy also is very nice. And also, if you go through TemPy, you'll find a lot of documentation, a lot of interesting information. So you can find some something useful here. Okay. Now, the thing that is interesting is that also there was this nice paper in 2011 by Poulan and Verstraete, where they talk about some kind of like the illusion of the problem of the exponential increased over the base space. And I think the main argument is this. Let's say you start from a simple state, okay? Maybe a product state. And then you evolve it, okay? How much time will it take this product state, when you evolve, to cover the whole Hilbert space, okay? And actually will take a time with this exponential in the system size, okay? So, means a time, exponential time to cover the Hilbert space. So this is, then you, this doesn't mean that this problem is simple, because as you evolve a system, the complexity still grows exponentially with the system size, okay? I'm saying about covering the whole Hilbert space available. So, oh no, wrong direction. So let's say if you have a full Hilbert space somewhere here, okay? Okay, there is a portion of states which are quite simple. We can call them area laws. Okay, and then as time evolves, they can cover a larger portion of the space, okay? But you evolve like for a time. This is typically polynomial in the system size, right? If you want to do a circuit, right? Maybe you do a polynomial number of steps. And so this is the space that you maybe can cover. And then there is all a large portion of the space that maybe for many experiment is not so relevant, okay? But then, okay, you don't know which part is relevant, how to reach it, and how to describe it. So it's still a very, very hard problem, okay? But I think this is a very, very interesting point, and I wanted to highlight this point to you. Then there is another point that I would like to mention. And this goes back to a paper in 2012, a very nice paper in Nature Physics, 2012, and Nature Physics. The leads, it's both a numerical, theoretical, and experimental work. The lead of the theoretical part was Scholwock, the person mentioned there. And for the experiment, it was done in the group of Immanuel Bloch in Munich. Both in Munich, actually. Scholwock is also in Munich. And here, they started this setup. The spin basically, oh, this doesn't work very well. Okay. Spin that you put up, down, up, down, up, down, up. Okay, so this is the initial configuration. And then they quench it, let it evolve, okay? And they measure the imbalance.
How large was the system?
Sorry? Okay. I don't remember the detail. Okay, let me think about it. I can look again. But it's a few tens, not
51.
50.
51.
Thank you. So now the problem, okay, so they measure the imbalance, which is spin at 1 sigma z at site L and sigma z minus sigma z at site L minus 1, plus 1, for example, okay? And then they look at the evolution of this thing in time. You keep getting the wrong one. Okay. It starts and it evolves. And so in the plot, there are two curves, one numerical curve, which is done with the DMRG, or matrix product states. Okay, so basically, okay, and then experimental points. Okay, so this is, of course, with error bars and so on and so forth. And at this point here, when I stop to do the continuous line, the simulations kind of couldn't go ahead, okay? And I will explain later on why simulation had to stop, why they couldn't fully trust the results anymore, right? We will get there. But the experiment could continue, okay? This is a nice example of already experimental setups who can do beyond what the numerics could do at the time. And so the funny thing, though, is that if you look at the trajectory, it's not that something super shocking was happening afterwards. Okay, it was fairly simple dynamics. It looks like some kind of damping oscillation. Okay, we don't know exactly how damped and so on and so forth, but it's not that the dynamic was particularly shocking. So when you look at this, you will think this should be in a sense easy to simulate, right? But you still are not able. We are not able to simulate this thing, right? And so maybe there is something that we're doing that still, we can improve, and maybe some of you will have some ideas how to improve on this. Yes. What is the what? X-axis and Y-axis. Time. And this is imbalance. Okay? Sorry. Thank you. Okay?
I have a question.
Yes, please.
By exploring the whole universe space, what is the measure numerically that you will? I mean, you told that for a area of state, like a product state, to explore the whole universe system will take exponential time.
Yes.
But what is the measure we can see?
Okay. Because maybe this is thank you for the question. Because Hamiltonian that they're considered is a local Hamiltonian. So it takes time for it to propagate, generate new Pauli operators, so on and so forth. Okay? The locality is very important in the case. Okay?
So in this case, what was the Hamiltonian under which it was?
This was something like in a Heisenberg model.
And the observable was basically difference between
Yes.
speeds.
Yes, correct. And it starts from a strong imbalance and you let it evolve. Okay. So in reality, in the setup, they had bosons, but they use very strong interactions so that effectively it can be mapped to a spin model. Okay.
It's just the system size which is restricting the
Well, as I will mention later on, as you do a quench and time evolves, okay, entanglement grows significantly, and from area law becomes a volume law, okay, and then the tensor network are not able to describe that. At least the MPS wasn't able to describe that. Yeah, I will go into the time evolution, and I will derive this more in detail later on. Okay, thanks for the questions. It's very nice. Okay, so maybe let's go to. I'll go to another board. Let's go to start to talk about tensor networks, and in particular matrix product states. And I will start here. Okay. So let's say a wave function psi, and I want to describe it in some basis of local spins. So I have sigma 1, sigma 2, sigma 3, all the way to sigma n. Let's do L. Okay. And this is a basis. You can choose whatever you want. In this case, basically sigma will take values 0 or 1. If I do spin halves, for example. Okay. So now my state in general will be written as a sum over all of these possible sigmas. Okay, this may be too small. So I can use the notation sigma vector, okay, to indicate the various sigmas, okay, or some coefficient sigma 1 with indices sigma 1, sigma 2, all the way to sigma L, okay? So this object here is the object which is some dimension of 2 to the L in general, right? And we can describe this as a tensor. Where I put sigma 1, sigma 2, sigma 3, sigma L minus 1. Okay. Instead of writing it as an exponentially long vector, I write it as a tensor which has exponentially many terms at the moment, if I write it exactly like this. And the point is that I could choose different configurations of the sigmas. For example, I can choose all of 0 or some 0, some 1s. Every time I get a scalar, okay? And I have all of the possible opportunities and combinations. Okay, so this is how we can describe a wave function. And then what about operators? Similarly, for operators, now I will have as a basis something like sigma 1, sigma 2, sigma 3, sigma L, and then sigma 1 prime, sigma 2 prime, sigma L prime. And here I will sum over all the possible sigmas, all the possible sigma primes, and I will have coefficients, sigma 1, sigma 2, sigma L, sigma 1 prime, sigma 2 prime, sigma L prime. Okay. And I can draw this, okay, in this way. Okay, so I will have sigma 1, sigma 2, sigma 3, sigma L, sigma 1 prime, sigma 2 prime, sigma L prime.
What is the meaning of writing it this?
Aha, yes. Okay, so this is what I'm trying to come to, okay, the way to describe this thing. So the way to describe this, as we will learn later, is basically showing you how to do certain type of calculations. Okay, but for now, do you see that this is a tensor or not? Otherwise, okay, let me do a step back, okay, and describe a bit more the graphics. I was gonna get there, but let me do it now. Okay, this graphical representation works in this way. A circle is a scalar. Okay. Then if I have a circle and a line, okay, this is a vector. Why is a vector? Here I can have many indices, okay, and so you can see this is a list basically, okay. Now if I have something like this, okay, this would be a matrix, okay, because I have a list of things here and another list of things, and I can reshape it as a matrix, okay. And so, as we will see later on, we can have other structures. For example, let's say you have something like this. Okay. This has 4 legs, so this is a 4-leg tensor. Okay, so why sometimes we put it horizontal, sometimes vertical? Here, it doesn't matter. But what matters is like the number of legs. Okay, so now, once we have this graphical representation, since you asked these questions, I'll continue. We can also think about operations that we can do. Okay, and so, for instance, if I take a vector, and then take another vector, which is something I can write like this. Okay, this is a vector-vector multiplication. Okay, and then you can think of doing something like something like this. This would be a matrix vector multiplication, right?
So the vector multiplication, there should be 2 times, outer product and inner product. It's like chronicle product.
Yes. It just, yeah, the product between, so in this case, the way you would do it, you write this as a vector, okay? This legs multiplies with this one, so it would be, this is here, we go and multiply this, and this leg will get these elements here, okay? And then you do matrix vector multiplication. Sorry?
Vector is the chronicle product.
Vector would be a scalar product that goes like this, okay?
The outer, the arrows are the opposite direction.
Sorry?
The outer product, like the cross product that you do.
You can generate, okay, so you can also build things that are, so if I take, sure. If I take something like this and something like this, okay, then you can build up a matrix, of course, okay? So you can see that these drawings actually start to get mathematical meaning. Okay, and then later on, maybe by the end of, by a good portion, when we are within some of the lectures, you realize, okay, I can interpret these calculations by looking at the drawing, or instead of writing the calculation, I can write the drawing. Everybody knows exactly 100% matching of what each thing means. Now, the other thing that is important is, let's say you want to compute an expectation value. Okay. So now we have the representation for psi with the representation for O, the operator. So O is here, psi is here. Okay, this is psi, this is O. And then psi conjugate. And like this you do the calculation. Okay, so far so good, but we have not done anything fancy. We're just rewriting the calculations that you will do, all the sums and the multiplication you will do in a drawing. But the point that these things are written as by the end of the lecture, hopefully I'll learn how to use this. The point is that you want to tap on linear algebra and find ways to compress distances, okay? And find ways to do all of these calculations faster, okay? And there are ways, especially in 1D, to do this calculation really, really fast, okay? And this is what I'm going to talk about. Other operations that are relevant, important to look at, is, for example, something like this. What does this represent? If you think about it, you have a different, is a trace, exactly. And then you get straight away that the cyclic property of the trace, okay? It really doesn't matter. So this is a trace. Okay, so now let's go I need to go back to this part. Okay. No, if I go up, then eventually we start to erase something. Okay. So when I was started to use tensor networks for machine learning, maybe if you're interested, I can tell you a bit about that too, although it's not part of the main lectures. I realized that there is a huge literature in a machine learning community of people using basically tensors or tensor networks or matrix product states or something similar with slightly different names. Okay, and you can tap on a huge background of literature in linear algebra. Okay, to describe how to describe different tensors. So let's say I have a generic state, okay, or something, okay, with many legs. Okay, how to represent it? And some of this interesting decompositions or way to look at it, I will just draw a few of them so that you're aware that they exist. Okay, so one of these is it's called CP decomposition. where you have some diagonal elements that couple some simple tensor of bond dimension 1. Okay, so this is one decomposition. Then there is something called Tucker decomposition.
This is representing state or?
Actually, any tensor you can write it this way. So this tensor could be representing a state, could represent an operator, could represent other things. This is just really generic about how to represent a multi-leg tensor. Okay?
Can you please repeat this part what you said?
CP decomposition. Something polyadic, I forgot what the system's for. Canonic polyadic decomposition, something like this?
Like what is this?
Okay, so you have a diagonal elements, and each element is coupled to a bond dimension 1 tensor. Okay? Or a more generic one, where you have a matrix coupled to bond dimension 1 tensors. Okay, this is the Tucker decomposition. Then you have this other decomposition, yes, which is known as, which we will play a lot with, where you have different tensors of this type. This has various names. The most common name that we use in physics literature is matrix pseudostates. But it's also known as tensor trains. Okay. Then you can take something like this, as we have here, and add a leg like this. This is assuming periodic boundary conditions. It's called tensor ring. And then you have other decompositions that are a bit hierarchical, which you can choose to do in different ways. Okay? Okay, so this is hierarchical Tucker decomposition. Actually, I'm not sure how to spell hierarchical. And then a very famous one in physics is what we call PEPS. For 2D systems. Okay, so it's tensor coupled together with the physical index coming out. Okay. PEPS. But in general, yes?
So what are the two big dots? Those are different in the CP and Tucker decomposition?
Oh, no, it's the same. These ones?
Yeah.
The big dots are different, yes. Sorry, let me go back. This one we impose that is diagonal. And this one can be generic. Okay. So this one also.
And these
Okay.
are CK.
So these are, sorry?
These legs are matrix or vectors?
Yeah, so every leg you have indices, potential indices, okay? But okay. But in general, you could write, the point is, given a problem, given a state or an operator, there may be a tensor representation that best, more efficiently represented. And so maybe you can come up with whatever other structure, okay? and see, maybe this turns out to be efficient, okay? Now, when I mean efficient, you need to think about two things. One is how well you can compress the information. Okay? And so this may depend on the geometry of the problem, the boundary conditions, and entanglement, correlation, and so on. So you think about, if I represent in this way, will I be able to come up with a lot less numbers to store in my computer, okay? Compression. The other thing that is very important and is not so straightforward, you may not think about it, is ability to manipulate this object and to extract information. It's not obvious that you can easily, in fact, whenever you will, as you will see maybe, whenever you have loops in your networks, it will be very hard to extract information, okay? But maybe easier to compress the information. So it's a bit of a dilemma. And I would like to give you an example of even in the same network, you can do calculations in two different ways, and it can cost you a lot more time or a lot less time. So this is a very nice example. Let me do it here. Okay, so I take a scenario like this. Okay, so I have a tensor A, B, and C. Okay, and now we have legs. So let's say A is a tensor with legs alpha, beta, gamma. Okay, then you have C with alpha, beta, gamma, delta. So gamma, delta. And then B has beta, delta, and then another legs we call epsilon. Okay? Now when we multiply all of these things together, you will see that you will get some object like this with legs alpha and legs epsilon. Okay, this is the only thing that come out. Okay, let's call this thing F. Is the final one. Okay, but I need to do this contraction. Okay, and how I can choose to do this in different ways. So I will show you two examples here. The first one is, okay, let me draw it again. I will just contract this first. Okay, once I contract this, I will get an object with legs like this, okay, and then I can contract again. Now let's think about this contraction here and assume for simplicity that the size of all of these legs is the same and is D, okay? So you have D, 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 D. All the legs have size D, okay? Now let's think about this multiplication here, okay? I have one index that contracts and one index is here. So this object C would be a matrix like this, D times D. Okay, this is my C. Okay, this is C. Okay, and now B. B, I will have one legs that contracts, and then I have two extra legs. So I will have something like this with dimension D here and D square here. Correct? So then, how many operations do I need to do? I will have this D times D is the operation. Okay, so the multiplication in the middle requires D operations. How many times do I need to do this? D times for each of these rows, and then D squared times for each of these columns. So it will take me D to the 4 steps. Okay? The last operation here it's something of this form. I have something of dimension D, D square And then again, d square times d. So how many operations is d times d square times d is equal to d to the 4. Okay, so d to the 4 order operations to do this contraction. Okay.
Then can you explain once more how are you doing the counting?
Okay, sure, of course. So when you do row by column, that's these steps, right? Now I have to do this for each row, so I multiply by this and more. And I need to do for each column, so I multiply by this square. Okay. So now, let's say, naively, I say, oh, I can do this in many other ways. But it's not true. I mean, yes, it's true, but it may not be efficient. Because let's say you consider this scenario here. A, B, C. And now the first thing that you do is to multiply these things together. Okay? So now you see A as two extras in this. You're contracting over on one dimension, but you have d square here. So you have d square times d. Okay? And then the other side you have d times d square. Okay, so the number of steps is d square times d times d square, which is equal to d to the 5. Okay, so you end up doing things in a more costly way. So this is to say that whenever we think of a network and something, think about how you're going to do the contractions and all the other things. Ken? Okay, cool. In fact, in some of the more recent and advanced results, the way they truncate and do the ordering and so on and so forth plays a critical role in getting some results that otherwise you will not be able to get. Okay, so not just the shape, but also the ordering and all of those things.
Do you think
Yes,
please explain once more how you're doing the...
Sure. Okay, let's do this example, which you did it a bit faster. So you have a leg here that multiplies with each other, okay? So this will be the leg that is shared, and they will do line by row by column, okay? But then this thing has two other legs here. So dimension of the other legs. So in a sense, let me use a notation that we'll use later, okay? Here I'm reshaping my tensor A into something as the one that I'm contracting is beta. So I will have alpha and gamma together on one side, and then I have beta on the other side.
So the beta is the index, which is B.
This will be the dimension beta, correct? And this side here is alpha and gamma. And then here again, I will have beta on this side, because now B, I reshape it in a way, maybe I do it here. I have beta, and then together, delta and epsilon together. Okay? Cool. Okay. So now that we are looking at tensors, let's think about what can we represent. Okay. So let's consider maybe a 2D system. Okay. And I divide this 2D system basically in the inner portion and the outer portion. And let's say this length here of all this number of legs here is L. Okay. So now how many, and of course I will have the physical indices coming out, okay? because it's a state, etc. Now, how many legs do I have in total that are broken? Okay, this is basically L to the power of 4, right? Yeah. Sorry, 4 L's. Okay, I have 4 legs. Okay, and each leg has d indices. So the possible type of combination that you have is d to the 4L. Okay, where d is number of indices in each leg. So what we want to try to say now is what kind of states can be represented by this kind of structures. And to picture this, what we can do is that we can represent, we can write the state psi as some sum of ij. Okay, now we have psi I on the internal index. So let's say internal, okay? And then j on the outside. And I call this psi I j, the coefficients, right? So I represents, maybe all possible types of sigmas that they can have, right? All the possible configuration which spins can be. And O is the same, but for the outer part, okay? And this thing obviously don't have to have the same size, right? They could have a lot less spins here. And I mean, this is generic, okay? You don't have to think about this. You can think about 1D as well, or whatever other dimension. You can do this. Now, and here this is a key step that in many of all of these calculations is once you have this psi ij, I can do a singular value decomposition. And the singular value decomposition is really the workhorse of tensor networks calculation in general. Singular value decomposition.
Psi is a d-dimensional vector.
Sorry?
Psi was a d-dimensional vector. Now you reshape it in terms of psi ij's.
Yeah, psi ij. Yeah, maybe the notation is not great. So let me use a different. Let me qualify. Can? I'm just saying coefficient that I label by the I and j. I is on the inside, j is on the outside. Is that okay?
In the left hand side, it's a d cross 1 vector, but in the right hand side, how the dimension matches. I mean,
these two don't have to have the same dimensions, I and j.
they don't need to.
No. So, okay, for any matrix, for any size, so that doesn't have to be square matrix, okay? You can always do a singular value decomposition where you will get, okay, so M, let's say, you get U as V dagger, okay? Where S is a diagonal matrix with entries which are non-negative, okay? So, and then this is unitary. U dagger times U is equal to identity, and is also is such that V dagger times V is equal to identity. Okay? So you can always do this. Now let's do this. It's not like when you do find eigenvalues, you can not always do that. This one you can always do it. Okay, so let's put this inside there. Okay, so I can write psi as sum of ij, and now let's use this notation. So I have u, I, and then let's say a, okay, s, a because it's diagonal, okay, and then I have v dagger, a, j. Okay, I can do that. So I will have a sum over a as well. And then here I have I on the internal portion, j on the external portion. Cool. Sounds good? Now what I can do is that I can group these things in different, anyway it's all finite number, so no, there's no major issues. So I will have a sum of A of this S, capital S, A. And then I have sum over I of U, I, A, I, internal. Sum over J, B, dagger, AJ, psi, J, outside. Okay? And what I'm going to do, I'm going to rename this alpha I, or AI actually, because it's A, I, and A outside. So I can rewrite it as SAA, A. Okay. And this is beautiful because this is basically Schmidt decomposition, okay? And the useful part of this is that all these A's are orthogonal with each other, all these are orthogonal with each other as well, okay? And now you can ask yourself, since they're all orthogonal to each other, you can truncate this, you can trace out, okay, from psi, you can write rho, okay, and rho is nothing but sum of A of this diagonal element square, very simple, A inside, A outside, A inside, A outside. Okay, and now you can trace out, for example, the outside. So ray inside, which is trace over the outside of rho, and this is simply sum of A of SA square. Okay, psi A. Good. So the reduced density matrix of just the inside, and actually the reduced density matrix of the outside is also straightforward. SAA square, A outside, are given by this indices. Okay, so how many of these indices are you going to have? Okay, so since we started from a matrix over there, psi ij, okay, which had 4. So the rank of this matrix at most, okay, is going to be d to the 4l. Okay, and if let's say you consider the more demanding scenario where all have the same weight, then you can even compute the entropy of this thing, which is minus ln rho, okay, rho I ln rho I, sum of I. Okay, since basically this is diagonal, you have all of these elements, yeah, then you're left with the sum of all of these things. And so this goes as over all of the elements. This goes as logarithm of d to the 4l. So it goes as 4l ln of d. Yes.
So the maximum bound that you get, this d to the 4l, that is corresponding to when all the SAs are independent.
Yes, when you need all of them, yes, exactly. It's the most demanding scenarios. Okay, so let's say the most difficult scenario that you can describe is something like this. Okay, now why is this interesting and also important? Is that first of all Okay, the dimension of the system is L squared. Okay, but the amount of entanglement you can keep is 4L, right? Which is related to the area law that we saw before, right? L to the d minus 1, so it goes as L. The other thing is that the bond dimension basically gives you a constraint of how much of this prefactor can be, and it goes as logarithm of that. So this is the kind of the limitation of what you can describe. Okay? Cool. Okay, nice. Now that we are here, let's look at a special case of tensor networks for the last half an hour. Time is flying. Okay.
If I want to describe the EPR modular integral state,
If you want to describe
modular integral states, then we cannot do this.
what states?
Modular integral. If you have a modular integral,
Module 1? Volume law. No, you can't. No, yeah, yes. And that's why, as, let's say, for example, you do a quench, then the entanglement grows, it becomes volume law, you cannot describe. Okay? But again, you could have, in your numerics, enough one dimension that you can describe it until a certain time. Okay? And eventually you will. Okay, so let's focus on matrix polar states for now. Okay, so it's something like this. In this case, the entanglement you can manage will go as the logarithm of the bond dimension, and that's it. Okay, you can only do a cut here. Okay, you have D there, and that's it. Okay, you can do better than that. So the other properties you can think of course, you can build. You can choose to have some periodicity or so on. But what is important, I think, is that they are dense. Okay, what does it mean that they are dense? It means that if you take a MPS with bond dimension D prime, where D prime is larger than D, and you compare it with an MPS with bond dimension D, so these ones can include all of these ones. Okay? So as you increase, let's say you have the space of the things you can describe. You have something with a certain bond dimension D. You describe the area of the Hilbert space that you can describe is something like this. With a bond dimension D prime, you will include, okay, when D prime is larger than D. You'll include all the states. So every time you increase the bond dimension, you shouldn't get worse, okay? You can improve, or you can describe all the states before you can describe all the other states. So this is nice and interesting. Now let's go to a problem. This school is called long-range correlations. And the first thing one of the first things I'm going to show to you is the matrix polar states can only describe exponentially decaying correlations. Okay, so, okay. Correlations decay exponentially. Okay, so let's do this. Okay, and this will be a good practice to some of the discussion we do later, also for graphical representations. Okay, so let's say we have an infinite state, just to make things a bit easier. Okay, infinite MPS. And now, let's say I have some operator here at position I. Okay, let's say call it L, maybe better. Okay, and then some operator here. Okay, at position L plus R. Okay, and then identities everywhere else. So this is simple, just identity. Okay, So the distance here between the two of them is this portion here is r minus 1, right? Okay, and let's say this operator is O, and this operator is O prime. They don't have to be the same, just generic case. And here's identity everywhere else. Okay. So now, what we're going to try to do is to describe the correlations. What I want to compute is basically O prime minus O prime. Okay? Cool. So how do I do this? Graphically, this would be this divided by minus divided. So this is operator expectation value for operator O, expectation value for operator O prime, but I need to divide by the norm, make sure that I'm doing things right. Okay.
Those are the local operators.
Sorry?
Those are local operators.
Local operators, yes. But I have two of them, they can be quite far apart, yes. Okay, so this is the calculation I need to do, okay? And I need to do this. Let me define some pieces of this puzzle. Okay, first piece of the puzzle I want to define is this object here, okay, which I call some E identity, okay? And this is a 4-leg tensor, and I can split it. What I want to do, and which can always be done, I can split it as a sum of I, lambda I, and then something like this. Basically, I'm trying to find these left and right eigenvectors, okay, and the corresponding eigenvalue. Okay, this is in general not diagonalizable, but I can write left and right eigenvectors and write it in this form. Okay, so.
Can you repeat that? What is the meaning of this equation?
Yes. Yeah, I'm getting there. So imagine you have a matrix. Okay, you can always write it as a sum of I, so lambda I, a vector like this and a vector like this. Okay, so this is what I'm doing here. But these vectors now has 2 legs because you have 2 legs. You combine them and you split them up after. Sounds good? Okay. Okay, so I write this as sum of I of lambda I, Ri transpose left I. Okay, so this maybe it's easy to see. Okay, that's fine. Okay, this is the first piece, and then we in the cases we have one value that extends upon the others, which is bigger on the others. Then you can write it as you can single it out. So you have lambda 1, R1, L1, and then you have all the others, sum of I different from 1, or lambda I, Ri transpose left I. Okay, then now you can see that when all the thing that is on the left, right, is it's like when you have transfer matrices, right? If you have infinitely many of them, there's only one that dominates. So everything that is on the left, okay, can be written as this left, so lambda 1 to the power of all the elements you have to the left, okay? Let's call it, let's call it alpha, okay? Then you have left 1, okay? And everything you have to the right, okay, you can write it as this R times lambda 1, or so let's say all the things that you have to the right, let's call them a beta number of them. So everything that is on the left and on the right of this thing would be described by very accurately, if you have a very, very large system, okay, by this, just the dominant vector. Okay, so this is fine. What about, so this is for the edges. And this is true above and below, okay, for all of these calculations. Okay, so now let's say you want to look in the middle, okay, this portion here. Okay, so you have something like this, okay, of length r minus 1, right? Okay, so then you have basically, you can think of it, you have this times this, this times this, this times this, many of them, right? And if you can write it down, since they're orthogonal, you can write this as lambda 1 to the r minus 1 times r1 transpose f1. Okay, and then you have all of the others. So we can group lambda 1, r minus 1 outside, then have lambda j. Okay, let me write it below because I need more space. The other one, maybe there are also some degeneracies, so let's use maybe lambda j omega, and I can take maybe the largest one. Okay, I have r j omega, left j omega, yes. Okay, and then here I have lambda j omega over lambda 1. Okay. The key point is that this will have this basis, okay, will be suppressed by the eigenvalue divided by the dominant one to the power r minus 1. And if r becomes very large, this will be suppressed significantly.
So, can you please repeat the strategy?
Yes, yes. So I want to decompose this calculation in various pieces, okay? So I will have whatever is outside here, okay, which is the same for everyone, okay, which is given by the dominant term here. Sorry?
Those square boxes, what do you do?
Square boxes here is the operators, this part here. Okay? So the state and the operator that I want to put in between the MPSs, and then a straight line means identity. Okay? So then you see you have a few different scenarios. You have this scenario here where you have a state, and then you have identity in this, which we are describing here. Okay, and we decompose it in this way. And then you have the portion with the operators I will describe later. And you have all of these other things on the sides. Okay? So now, what I want to show is that the outside is the same, but inside you have these things that decays.
Can you repeat the edges?
The edges, sure. So think of this. Think of it as a matrix, okay? you can always write it in this form where you have right eigenvector, left eigenvector. Okay? And then, so you have lambda I. But now, of course, you decompose it as a tensor. You can write it as this, Ri lambda I. Now, let's say you multiply many times. Okay? Then the largest one will be the one dominate, the only remains. Okay? So that's where we are. Okay. So now that we have this, boink.
But how are you sure that there is going to be one largest one?
Okay. Yes, I think this is ensure when you have gap systems.
Okay.
Yeah. And in fact, this is why it's not a problem, what I'm going to show to you, because in gap system, the correlation decays exponentially.
So, can you also please tell what this expression exactly?
Which expression? The drawing there?
You wrote that lambda 1 times r to the power minus 1 is expression.
This one? Okay. So I'm trying to describe the correlations here. So you have this times this times this times this, right? Each one you write it as you have r sum of I of Ri dagger left I, right? Yes. Now you have all of them. But once you fix one Li on one side, because they match together, then you have a product of all of them.
Now I'm trying to understand where the information about the O is going.
I haven't put it in yet.
Okay.
Yes. I'm getting to that later. Okay. So now I describe first the edges and what happens in the middle, and then I'll describe the whole. Then the whole, yes. The whole, I will call it this portion here, where the operator is. Okay. I will describe this some EO. Okay. Okay. For O, and EO prime for O prime. Okay? And what this does is to couple Li and Rj's that they were not coupled together before. Okay? So this will allow couplings between the left, right, and right eye. Okay. So now, here we can try to write the full expression, and you have two terms. Yes. Okay. Okay. So first, this would be approximated by this Li L1 E0 R1 L1 E0 R1 Okay, I've read the expression and I will explain it.
So this largest eigenvalue lambda 1, it is of the Hamiltonian or which?
No, it's not an Hamiltonian, it's a state. There is no Hamiltonian here, right? The only operators have this operator observable that I want to estimate. Okay? O prime. And then I have some state, okay? Some infinite state and maybe periodic infinite state, okay? So now you can see once you look at this O prime, okay? It's given by the E0 that doesn't couple to other r's, so it keeps the same r. Okay, and the only thing, and so all the lambda 1s that are inside the system and outside, they are erased, and the only lambda 1s that are left in the norm are those at the site of O and O prime. Okay, and then you have all the others. So E0 could couple to other basis elements here. So let's call it omega, because maybe the first one is some degeneracy omega. And then only in this case you get the lambda 1, and you have this prefactor here in front, the second largest decay eigenvalue divided by lambda 1. So you have this decay here. Okay, does it make sense? Let me try to describe it graphically. I should have put them in a different. So here I have all the lambda 1s, lambda 1s, lambda 1s here. Here all lambda 1s, okay? Inside here, I could have lambda 1s when E0 coupled to the lambda 1s, or I could have lambda 2 and all the different degeneracies of lambda 2 inside here, okay? So this will give a term, this term here, that decays exponentially. With the size. Okay? So this is the portion, the non-connected portion. And then if we just look at O or O prime, okay, that is actually this portion here. This term here, if you let's look at the drawing now. Okay, so this thing here is just lambda 1 E0 R1 divided by lambda 1. And this one is L1 E0 prime EO prime R1 divided by lambda 1. So this term here is exactly O prime. So now when you take the difference between the two, you're left with this. Okay? And so the correlations between the correlations, they are bound to decay exponentially. Okay? And the correlation length, of course, depends on the ratio, the logarithm of the ratio of lambda 2 over lambda 1. Okay. Cool. Is this a big problem? As I said before, there are states which have these properties. They can be described exactly. The other ones, you just need to pile up enough bond dimension D that you can describe them. Okay. Cool. 5 more minutes, is it? Mamma mia. Okay. Can be degenerate. That's why I'm doing the sum of these omegas. Yeah, can be.
So the lambda 1, it
Lambda 1 not degenerate. Lambda 2 could be degenerate. So I'm looking at some.
maximum eigenvalue you are saying.
Yes.
Like, let's say, and that corresponds to that product, this EI.
Yes. So EI will have one major one and then all the others.
And EIs are those products. Between
Yes. Yes.
connected by some eigen.
Yes. Yes. So now it looks very complicated because we need to take into account of the portions to the left and to the right in this fashion. But we'll show later that there are ways to simplify this calculation significantly. I guess on Wednesday. But before we call it a day, maybe let me cover one more thing. Yes, and then I think it's a good place to stop. And since we talked about this calculation, these sums, and what I would like to do now is to say that, remember when I told you before which tensor to use, I say you want to see how well they can compress, but also how well you can do the calculations. Okay, and in tensor networks in tensor networks, in matrix product states, you can always do all the multiplication, contract all the tensors efficiently. Contract efficiently. And let me do it here. So let's say you have something like this. Okay, so what are the dimensions here? For this leg, this is the physical dimension, so sigma. Okay, and we call it small d. Okay, and this is the auxiliary dimension, we call it capital D. Okay, so you have capital D here, small d, capital D, small d. Okay, and you have what is interesting is that if you start, let's say from one of the sides, let's say here from the left, I'll show you from the left, you can always compress these things very efficiently. And let's do it, yes, let's do it this way. First of all, I will compress these two. Okay, so here, how many operations will I need to do? I have D, because I have a leg. The system is something like this, right? I have D and small d, and then the other tensor is small d and big D, correct? So now when I want to do the multiplication, I will have something like dimension D here, D here, D here, and D there, right? And so it will cost me D times small d times big D, similar things that we did before, right? So it's small d, D square. Okay, not too bad. Now what do I have? I have something I've merged them into one big object here with big D here, and then I have something here. Okay, so I've merged them into one object here, and then I have one dimension D here, small d, big D, correct? And then continues. So now we can merge these things. Okay, so how much is going to cost me? I have this thing here as I have an object like this with D, and small d, okay? And then I have another object here which has dimension big D and big D. And I'm contracting over this one here. Okay, this is what I'm doing here. So this is going to cost me D times D, small d times big D on this side, then D here, and then I have D here, and then I have D here. Okay, so it's going to cost me D, small d, big D cube. Okay, and then once I do this, what do I have? I'm left with something, a big blob here, connected to this. And now, here I have a bigger leg, okay? Because I have a D and small d, D and D. Okay? Now, similar. I have dimension here D, I have dimension D here, and this one is dimension D here and D here. So multiplication is going to be D times DD times D, which is again DD cube. Okay? And all the operations you continue like this, it will always at most be of the order DD cube. Okay? So you can compress all of these things and get to eventually at the end to a scalar. Okay? You will end up at the end something like this, and then you get a scalar. Okay? And at most the cost of the calculations will be DD cube. Okay? Very, very efficient. This is the fantastic thing of matrix polar states. Okay. Good. So I think next class I will talk about how to make things even better. So with canonical form, and how to compute the ground states, and hopefully we can get also to time evolution. If I don't get to time evolution next class, I will still have a third class, and then we'll start to neural quantum states. Okay. Good. Any other questions? Please.
How did you get this lambda 1 square? Or can you just tell me how do you calculate O prime?
Yeah, because when E0 is happening, okay, this operation here, I should have split this between left and right, so I didn't have to go up and down. Sorry. I will try to use my board, but next time. But okay, so here, let's say this system has n legs, okay, a very large number of n legs. Okay. So you'll have lambda 1 n times at the bottom. At the top, you'll have lambda times n times minus 2, because in these places you have E0 or E0 prime. That's it. That's why you get lambda 1 square. Okay? Cool. Same for these calculations. You have lambda 1 n minus 1 times on the top, and lambda 1 n times at the bottom. And so you get 1 lambda 1 for each one of them, and so square. Okay?
And why did you have just go down?
Yes.
Yeah. So two indices, omega and mu. Right?
Yes. I got a bit messy here. No, not so bad. Yes, this is omega. Because in my notes I wrote mu and then from 1 to omega degeneracy, sorry. So it's omega. So this is because the second one may be degenerate. So this is the sum over the degenerate of the second eigenvalue.
Why do you pull out this lambda 2?
What do I pull out? Where does it come from? It comes from E0, okay? E0 can couple lambda 1s to lambda 2s. So sorry, the left L1 to R2. Because this is different tensor, right? Yeah. So it's not diagonal in general, okay? It could be, but it's in general not diagonal in this basis here, right? So you can couple different ones. And that's where you get correlations. Otherwise, you will have no correlations at all, right? So this can couple in between, and that's. But once you couple to let's say in between to lambda 2, some base, the second basis, then throughout will be the same, right? Because this is orthogonal, and you can follow through, and then that's where you get this time. Okay.
You can couple to other lambdas also. Why lambda?
You can okay, you can couple to other lambdas, but again. Approximate, okay? Since it's many, I say, okay, the most important one with the second one. The other ones will be even smaller. The impact will be even lesser. Make sense?
So here you just make it an approximation that lambda I by lambda 1 for I greater than 2 is very small, so that's why the factor can be neglected. But
so here, at this point here, I say the lambda 3s and the lambda 4s will be neglected compared to lambda 2s. Lambda 2s will be the more important one. I just keep that one. But the lambda 2 can still be degenerate, so I keep a few of them.
right, so this second order term, this lambda 2 by lambda 1, this whatever the sum is, that can be further approximated if you think that the correlation became exponential and so on.
So this actually gives exponential correlation. This thing says exponential correlation. You see, it goes as this goes as some number lambda 2 over lambda 1 to the distance minus 1, okay? Then you can say, okay, so this is an exponential of the distance over some chi, and then you find what the value of this is, which is be related to logarithm of these things, okay?
So when you derive that decaying correlation, you have to assume that the unique eigenvalue, the maximal eigenvalue is unique, right? What if
Yes.
you have a degeneracy?
So here I'm describing the states that can be done exactly with matrix polar states, and which are for a gapped Hamiltonian, and there you will have just a single one. So if it's more, then you will already not be able to describe it exactly. Okay, so this is what can be done.
You
said that MPA scales as D cubed.
The adding up, this is when I want to compress all this and I try to compute how many steps each time. So d cube and then roughly L times because you have L of them. Okay, so this is the amount of calculation. But each calculation will not cost you more than d cube unless you do things strangely.
This is better than other methods.
Oh yeah.
How does the other methods?
Yeah. So let's say you take 2D systems. Then it's very, very hard to find, actually, it's the problem of contracting 2D problems is P sharp, okay? And because let's say you start and you compress this, already you have so many legs open, right? Okay, and then you have to sum up all of this. So you always have a lot of legs open. Here, at most you have 2 legs open, and that's why we get the d cube. Here you have a number of legs open that scales with the size, one of the dimensions of the system. So it's extremely difficult. It's actually P sharp.
So let us thank Dario and maybe software.